the proton center is, okay? And so if in the second case, there's going to be a center of negative charge and a center of positive charge. Yeah, do I need to draw a picture, or you're following? Following, okay, if somebody tells me, I'll draw a picture. So then what happens is that there is a positive location, that center of positive charge, and a center of negative charge here. And so basically, even though the whole system may be neutral, and if you go very far away, you are not going to see any Coulomb field because the system doesn't have any net charge, right? You have a positive charge here and a negative charge here, they add up to 0. And even though you go far away, you don't see any field, clearly there must be some electric field. Well, I erased that expression, but because there are charges and they're located some places, so there is going to be an electric field. So what is the electric field produced by that configuration? Maybe it's very complicated, but for example, let's try to simplify. What is the electric field produced by that configuration of charge if I go very far away? Okay? So if it's not going to be a Coulomb field, what is going to be? And it turns out that for this particular type of situations, there are many experimental situations that can be explained properly by assuming that the separation between the positive and the negative charge is very small. And the reason for that is because the instruments that you typically use to probe this liquid are much larger than the separation between the charges. You cannot measure the separation between the charges. So what you can measure is the effect of the separation, but you cannot measure the separation itself. And so, all right, so that distribution of charge when two positive and negative charges are very close together is called a dipole configuration, okay? Probably everybody knows about that, but dipole descriptions are extremely useful. But what is more interesting is the next thing I'm going to tell you, because so far maybe dipoles everybody knew. But maybe there are some atomic arrangements that are more complicated than just two charges. Maybe there are 10 charges, maybe there are 100 charges, okay? Maybe there is a very complicated cloud of negative charge around it. But even in that case, when the net charge of the object is going to be 0, you still can find far away a dipole effect. So even if in reality they are not a positive and a negative charge, you can still have a dipole effect, okay? And so with this intuition, and I hope it will become better as we read more, the concept of a dipole can be generalized to more complicated distribution of charges. And the point is that any arbitrary, completely arbitrary distribution of charge, doesn't matter if it's a dipole precisely or if it's a quadrupole precisely, any absolutely arbitrary distribution of charge, I put them, that are confined in a certain region in space, can be expanded in what is called a multipolar expansion. And so, and if we are relatively far away, as is the case in many practical applications, then maybe 1 or 2 or 3 terms are enough to do what I want to do with those fields. So it's very important to understand this multipolar expansion. So what we are going to do is that we are going to first, number one, do the exact dipole electric field expression. We are going to find the electric field for a dipole. And once we do that, that's relatively easy. Once we do that, we will move on to the very general charge configuration and prove that it doesn't matter how arbitrary the charge configuration is, the two more dominant terms are going to be the monopole, which is the Coulomb term, and the dipole term. And then there are going to be other terms. So what does it mean, all this mess? It's going to be clear as soon as I show you the details. Okay? So let's do the electric dipole, okay? First. And this is going to be already starting with the electric dipole, but I'm going to first talk about the precise mathematical dipole, meaning two charges that are very close together. Okay? So this is a very specific situation. And then we're going going to get rid of that assumption, and we're not going to do it in general. But this is a very good opportunity to practice what we just learned, that we really don't need to do the electric field. We can do V, and later on we see what it takes to retrieve the electric field, by taking the gradient. Okay, so let's go and let's get to work. Okay, so let's consider. So this is the general topic. Let's get started by doing the, let me call it mathematical electric dipole. Okay, I call it mathematical just to make sure that we understand that this is an abstraction, and in reality, most likely we're going to have very generic distribution of charges, but we're going to make the connection later. Okay, a mathematical dipole is nothing but two charges, plus q and minus q, separated by a small distance. That's what the mathematical dipole is, period. Okay? There are not that many of those in reality. But we'll see that it's important to understand that anyways. Okay? So, all right. So let me then do the following. Let's take a frame of reference, x and y, and at location r prime, I'm going to locate my tiny dipole, which I'm going to actually exaggerate the picture so you can see what I'm talking about. And so remember that our sources are always located at r primes. That's the notation we are using. And I'm going to make the observation point at position r, as usual. Okay? So this is going to be my sources. And I'm going to observe from here. Okay, that's the observation point. Okay, so I'm going to put here, precisely at r prime, a charge minus q. And then I still need to put a charge q to make the dipole somewhere, okay? And so I'm going to do it like this. So over here I have minus q, and I'm going to put q here. And this vector that I drew is supposed to be very, very, very tiny. And I'm going to call it L. I'm sorry. Okay. All right. Plus q and minus q. In reality, both of them are located at r prime because the quantity L is tiny. Okay. I don't know. That's it. I can call it many things. But okay. So remember, in physics, to say that something is small is really not that good because L has units of meters. So if you measure the quantity in meters, maybe 10 to the minus 8. But if you measure it in microns, then it's going to be only 0.01. Okay, so what is small, we'll have to be careful, and I will define. So in physics, as opposed to in mathematics, things are small only in comparison. Something is smaller than that something else. So that's the proper way to do it. Okay, so so remember, then somehow I want this quantity L to be small. So the charge minus q will have an effect on r through this vector here. So the vector that joins minus q with the observation point. And the charge plus q will have an effect to this other vector. Right? Okay, so it's getting very crowded, but since minus q is located at r prime, then the vector difference between the observation point and minus q is nothing but r minus r prime. That's easy. For plus q, then the vector difference between r and that source is r minus r prime plus l. Okay? So I'm gonna write that explicitly. No questions? Okay. So then, okay, so we had that our, oh, great. So our electrostatic potential at the observation point is always equal to 1 over 4 pi epsilon 0 sum qi over r minus ri. This is always. So we can start from that. And in our case, now in this particular problem, there are only two QIs, Q1 and Q2. Okay? And so this reduces to 1 over 4 pi epsilon 0 times, okay, so the positive charge, well, of course, is plus Q. And at the bottom, we have R minus Ri, which is the location of the particle plus Q. And that is R prime plus L. Okay, so it's going to be minus R prime minus L. That's the Coulomb effect of the charge plus Q. And then plus, the second charge Qi is negative. This one is negative, so it's minus Q over the absolute value of R minus, simply in this case, R prime. Okay?
Why is it minus L not plus L?
Oh, yeah, because, okay, very good. So R1, which is the positive charge, you got it? Okay, okay, fine. Okay, so we have that thing, okay? So, in principle, since L is small, somehow, in a way we are going to define, those two terms will cancel each other out, right? Because we have Q over R minus R prime, and this is tiny, plus or minus Q over R minus R prime. So those two terms are pretty much the same, and they will cancel. Okay, so this is, okay, but it cannot be zero because we know that if we have two charges, somehow eventually we'll see an effect, correct? So for example, if I went to the center between the two charges and I put a test charge there, then it will be pushed toward the negative charge. So the field cannot be zero, correct? Okay, so somehow we need to deal with that. So, okay, so let's clean this a little bit, and so let's write like this. So we have 4 pi epsilon 0, so we don't write it too much, times V equals Q times 1 over the absolute value of R minus R prime minus L minus 1 over R minus R prime. Okay, and so
how do you introduce the V?
what's that?
How do you introduce the V to the equation?
It's already here. I just move the 4 pi epsilon 0 so we don't write too much. So I'm going to deal with this expression on the right hand side, okay? So the what I want to do now is to study this part of the expression, because if I'm not careful, these two terms will cancel each other out. So that I want to pay attention to that term that has an L and see how we solve this riddle of not erasing important information, okay? So let me write it over here. Let me work with that thing. 1 divided by r minus r prime minus L is equal to r minus r prime minus L to the minus 1. Okay, fine. So I haven't said anything interesting so far. But the next step is interesting, because the problem is that we have a complicated, a very general vector expression there, and we need to compute the magnitude before we take the inverse. Well, it turns out that there is a very general way to compute the magnitude of a vector, whatever the vector is, simply by doing the scalar product of the vector with itself. Because if I multiply scalarly a vector with itself, I get the magnitude squared, correct? And so if I take the square root of that, I'm done. Okay, so what I'm saying here is that given any vector whatsoever, any general vectors, if I do this, the answer always will be the scalar A squared. Because it's by definition of scalar product, you get A times the cosine of 0. Okay? All right, so I'm going to make use of that, and that will simplify a lot the computation. So this absolute magnitude, I'm going to write it like this: r minus r prime minus L dot itself. R minus r prime minus L. And I know now that that thing that I just got there is the square of the magnitude that I want. So I have to take a square root now. So I already had a minus 1, so it becomes a minus 1/2. Okay? And now we work it out. I can take r minus r prime all together. You see? And in a second I will justify why I'm taking r minus r prime. I'm not doing 3 terms by 3